Hello, we are going to approach the 15th lesson of the course dedicated to induction coefficients. This lesson consists of three main points. In the first two, we are going to see the concepts and properties of the mutual induction coefficient and the auto-induction coefficient, and then there will be a last moment in which we will develop a practical example. Let's imagine that we have two electrical circuits. One has the contour that we are seeing right here. That is, it is a wire with this circular shape, and another one has this star shape. It does not have to be specifically this exact shape. The star means that the shape could be any. What truly matters and what it is going to be relevant is the shape that they have and where they are placed and with what orientation. Well, if through the first one of the circuits an electric current circulates, that means it is creating a magnetic field. As we already know that it follows this formula to obtain it. In each point of the space, one would have to apply this equation of integrals and obtain the result. I am specifically interested in the magnetic field in this whole bunch of points, not in the rest. Why am I interested in these points specifically? Because my goal is to obtain the flux of the magnetic field created by the first current through the second circuit. And in order to do this then, on this bounded surface, we will have to do the integral of the magnetic field. The equations here can get quite complex, as we already know, from the second section of this course, and here what I want to see is not their application, but what happens, how all this varies if the current in the first circuit changes, specifically if it is being multiplied by a certain factor k. In other words, here the point would be that the current that circulates is k times greater than the original one. For example, the graphical representation here is made with a factor 2. The current is doubled, but now we are talking about a generic k. In that case, I can calculate the magnetic field created at any point by this new current. We can observe that in this situation, the only change is that you have to replace I with I prime. Since I prime is represented by k and k is a constant due to the periodicity of the integrals, I can factor out the constant. This directly yields that the new magnetic field is k times the original. In other words, when the inductor current is multiplied by a certain factor, the magnetic field is also multiplied by the same factor. The same principle applies to the flux, as we can see in this derivation. For similar reasons, if the new field at any location is considered, you can multiply the previous one by a factor k that can be taken out of the integration. Consequently, you obtain the new factor. For example, if the current increases fivefold, all magnetic fields at every point will increase fivefold, and the flux will also increase fivefold. So, these two ratios, the new one and the old one, and the new intensity and the old one, share the same factor k. Therefore, this ratio is equivalent to the other one. By rearranging terms, it becomes apparent that the ratio between the flux of the second circuit and the intensity of the first one remains constant, regardless of any actions taken. As long as circuit positions are not altered, current is not applied in a different manner, and no modifications are made. Well, so this constant that is characteristic of this pair of circuits receives the name of coefficient of mutual induction. Why does the word induction receive all this? Mutual is obvious because it is between two. Coefficient because it is a constant. What is that induction? We'll see its meaning in a moment. And here we would have the definition. This is all about how the first current circuit affects the flux of the second one. The circuit that drives this whole process is usually called the primary, and the one that receives that flux is called the secondary. So what we have got here is a relationship between the electric current flowing through the primary and the magnetic field flux due to said current, but through the secondary instead. Well, the unit is called Henry, in honor of Mr. Henry, who worked extensively on these matters, and it is written with a capital H, as is customary whenever a unit is named after someone. The definition, as befitting a coherent system, states that 1 is equal to 1 divided by 1. So the Henry is essentially the Weber divided by the ampere. Now we understand the reason for all of this and why we are interested in that coefficient in the first place. Specifically, if the primary current is not constant but varies instead, it will result in a magnetic field that varies in the secondary current, a flux that is going to change. Therefore, in the secondary, an induced electromotive force and a current will appear. In other words, this variable current causes a new current to appear, a current of its own within the secondary. Basically, that's what transformers do. Well, applying the already mentioned equation, the Cayley-Faraday. To be more precise, where it says flux, we substitute mi. Since mi is constant, we can add it to the derivative, resulting in the following relationship. The very relationship that encompasses all the aspects we are currently exploring here. That when the current varies at a certain rate in the primary, it is enough for me to multiply with the coefficient of mutual induction and change sign, and I have the electromotive force that all this is inducing in the secondary. Everything we are seeing about how the primary affects the secondary can also be that it is a circuit on itself. After all, if a circuit has an electric current, it creates a magnetic field that also circulates through its own bounded area. Therefore, as before, we would have that if this electric current is multiplied by a factor, this magnetic field grows by the same factor, and the flux through itself grows by the same factor. Therefore, the quotient between the flux and the intensity, in this case, it will also be constant, and therefore it will be represented by the letter L, and it is also called the self-induction coefficient. Well, the unit remains the same because there is no reason to change it. It is still a Weber divided by an ampere. Therefore, both coefficients, mutual induction and self-induction, share the same units. Regarding the development we discussed earlier about shunting, it is exactly the same if the current in this circuit changes. It will result that appears an electromotive force induced on itself. Well, this self-induced electromotive force is obtained by derivation, and simply by doing the same development as before comes out exactly the same result just by changing concepts. It is not intensity in primary causes, using the coefficient of mutual induction or an electromotive force in the secondary, but a current in a circuit using the coefficient of self-induction allows me to obtain the self-induced electromotive force. Let's take a look at an example of the application of the first part of a double circuit, which can be an example of a transformer. Through a circuit, the primary circulates an alternating current with this expression of intensity, that is, the typical 50 Hz, oscillating between minus 0.2 and 0.2 amperes. As it is a variable current, a variable flux will appear in the secondary. What we want to know is how is the current that will appear in that secondary. Knowing that the mutual induction coefficient is 0.05, it is as simple as applying the equations that we have already seen. In the second circuit, minus m derived with respect to t, m is known. The expression of the intensity as a function of time we know. Now we just have to derive 0.2 times cosine of 100 pi times 100 pi, which is the derivative of the inside, and we have this expression, minus 3.14 cosine of 100 pi t. That is to say, we can verify that in the secondary, we have an alternating current of the same frequency as in the primary, but with the potential difference oscillating between minus 314 and 3.14 volts, with a little more complication because you have to put some ferromagnetic elements with what are called cores to better conduct the flux. Let's see. This is the essence of the operation of a transformer. Let's finish it up by simply restating the summary slide with everything we have seen. Firstly, we have the definitions of the mutual induction coefficient, like this ratio, and the self-induction coefficient, and then the properties by which those coefficients are relevant in terms of how they affect an electromotive force in a secondary or a self-induced electromotive force. Well, thank you very much for your attention, and good luck with the upcoming class.